Hey, this is Bottom, and last time we talked about this. We talked about Nash equilibria. So this time, we're at the theory, part 5. We're going to do an example of a Nash equilibrium. So there's a general procedure for how to calculate a Nash equilibrium, and we're not going to do that. We're going to do that a little bit later. For now, we're just going to figure out the Nash equilibrium for rock, paper, scissors. And the way we're going to do this is we're going to guess the right answer, and then we're going to show that our guess is actually the right answer. So our guess is that our Nash equilibrium is 1/3, 1/3, 1/3. And like I said, this is in fact the Nash equilibrium, where both players are playing 1/3, 1/3, 1/3. All right. So why? So this is really an exercise in checking that this satisfies the definition, right? So recall the definition. Nash equilibrium is a pair of strategies that maximally exploit each other. So we're going to show that 1/3, 1/3, 1/3 maximally exploits 1/3, 1/3, 1/3, and vice versa, of course. So to do this, we just have to backtrack and go through our definitions, right? So what does it mean to maximally exploit something? When you max exploit, when we maximize our expected value. So, all right, well, let's calculate our EV, right? The EV of 1/3, 1/3, 1/3 versus itself is 1/2. You can do the calculation. It's fairly tedious because you've got 9 possible outcomes. The faster way to do it is just appeal to symmetry. Say that, well, you're both playing the same strategy, so it wouldn't make sense for one player to win more often than another, so you both have to win half the time. So the next thing to do is to check this lemma. I'll write it as a lemma. So a lemma is a statement of truth of minor importance, as opposed to proposition earlier, which was a statement of truth of moderate importance. So lemma every strategy has EV 1/2 versus 1/3, 1/3, 1/3. And the question is, why? Why is this so? So here's how we're going to prove this. We're going to check for each pure strategy that each pure strategy has EV 1/2 against 1/3, 1/3, 1/3. So let's do that. Let's say that we throw a rock. So SP, short for suppose. Suppose we throw a rock. All right, well, what happens? A third of the time, they throw rock as well, and we tie. So that's EV 1/2. Then a third of the time, they throw paper, and we get nothing. And a third of the time, they throw scissors, and we get 1. And so all of this adds up to 1/2. So the EV of rock is 1/2. Great. And now, of course, for paper and for scissors, it's going to be the same story, right? It's going to be exactly this equation. Just this will be a 1, this will be a 1/2, and this will be a 0, and or the other way around. And so all the pure strategies have EV 1/2. So now what about the mixed strategies? Well, what's going to happen is you've got a mixed strategy that says play rock with such and such probability, play paper with such and such probability, and play scissors with such and such probability. You can go into random.org, generate a random number, and then play the corresponding pure strategy. Well, no matter what you roll on random.org, you're going to end up with a strategy that has EV 1/2. So your overall EV has to be 1/2 as well, right? Because no matter what random.org tells you, you're getting EV 1/2. You're winning the game half the time. So that means that all strats have EV 1/2. And so this proves the lemma. So that means that, well, in light of this observation, every strat maximally exploits 1/3, 1/3, 1/3. Right? Because everything has EV 1/2 against it. So the maximum EV you could ever have against 1/3, 1/3, 1/3 is 1/2. And every strategy achieves that. So this is perhaps a little bit bizarre. I find it a little bit bizarre. So I'm going to put an exclamation mark there. And in particular, it means that 1/3, 1/3, 1/3 maximally exploits itself because it achieves EV 1/2 against itself, and you can never do better than EV 1/2 against itself. So there you have it. There you have two strategies that maximally exploit each other. And so that means that 1/3, 1/3, 1/3 is a Nash equilibrium of rock, paper, scissors. And it turns out that 1/3, 1/3, 1/3 is in fact the only Nash equilibrium of rock, paper, scissors. Every other strategy, or every other pair of strategies, has one that can improve to exploit the other a little bit more. So this is maybe a little bit remarkable. I find it a little bit remarkable. And it also highlights how Nash equilibria can be a little bit unintuitive, right? Even for a very simple game like rock, paper, scissors, we had to do some amount of work to check that this was in fact a Nash equilibrium. Because Nash equilibria are so, not bizarre, but unintuitive, it might be useful to say a few things about them. One thing we might wonder is, do Nash equilibria always exist? And the answer is yes. In every game, there's at least one Nash equilibrium. And this is a theorem. So a theorem is a statement of truth of major importance, and it's due to Nash, hence the name. And I believe this was in his thesis in 1960. So this was, there was a special case of this theorem that was actually proved before Nash by von Neumann. And in fact, that case would be sufficient for a lot of our applications, but the full theorem is due to Nash in 1960, and that's the celebrated one. And the proof Well, the proof is complicated, but there's a joke answer where von Neumann famously said that this was just a just a fixed point theorem. I believe there are two ends. So this is, of course, not a real proof, but it is true to some extent that a lot of the proof of this theorem is comes down to a fixed point theorem. So the proof is not all that complicated. I believe Nash proved it in only one page. So for the very curious people among you, you can go look it up. I think that his thesis is easy to find.